Hi guys, and welcome back to my channel. In this video, I'll be going over the SChO Silver Problem 3 from the 2021 test. So this question was basically like a mass charge balance sort of introductory question. I thought it was pretty straightforward. Usually in mass charge balance problems, the hardest part is making assumptions on what to eliminate out of equations, or say something is like very, very small, some concentration is really small, you can sort of exclude it from an addition or something, like these sort of assumptions you have to make. This question sort of gave you the assumption already, so I think this was a really good sort of introductory mass charge balance question for someone who is just starting to learn what MCB is and how to solve MCB problems. So let's sort of just get right into it. As you can see, this is a question on the chemistry of coral reefs, and there's a lot of background information that this problem gives. There's a lot of writing, but it's actually not a super long problem. So we're just talking about coral reefs in the ocean and how different pH levels can hurt the coral reefs. I'm not going to read all of this because it's pretty long, but yeah. So basically the important thing is if the water temperature rises or the pH drops, the algae are secreted from the corals, and without algae, the corals lose their food source and they slowly die. So it's basically talking about how the pH in the ocean is changing and how this can be bad for aquatic environments, and especially coral reefs. So let's get into the more actual part of the problem. There is carbon dioxide in gaseous form in the atmosphere. This carbon dioxide will be in equilibrium with dissolved carbon dioxide in the water. So we're given some sort of equilibrium here, where we have gaseous carbon dioxide and aqueous carbon dioxide in equilibrium. We're given the K constant, so that's our first sort of equilibrium. The dissolved carbon dioxide can react with water in the following equilibria adjusts. So we have CO2 reacting with water to form carbonic acid. This is a common reaction. You should sort of be familiar with this. So we have this reaction as well. So you can see that the more CO2 we have in the water, the more carbonic acid we will make, and that will lower the pH and be bad for environments. This is why we sort of want to reduce our carbon dioxide emissions, right? In water, H2CO3 is a weak acid that is part of these equilibrium. So we have two different dissociations. It's a diprotic acid. So we have Ka1 for the first dissociation and Ka2 for the second dissociation. So here we can see there's this diagram for H2CO3. And I didn't know what this diagram exactly was when I was solving this problem. So the important thing is to be able to interpret this diagram even if you're seeing this sort of thing for the first time, right? So you can see that we have pH on the x-axis, and we have the fraction of the species on the y-axis. So let's look at this diagram. We can see at low pHs, right, low pH, we have high fraction of H2CO3. That makes sense. At low pH, if we think about Henderson-Hasselbalch, we'll have a lot of the protonated form of our acid, right? And say as we increase the pH, we have high, so at like slightly higher pH, we have high concentration of HCO3 minus, right? That makes sense. When we have a slightly basic environment, we're going to have a lot more of the base present rather than the acid. And if we have really high pH, we have very little of HCO3 minus, basically no H2CO3, and high amount of our carbonate, right, CO3 2 minus. So as we increase our pH, right, we go from, okay, at low pH, it's really acidic. There's going to be lots of the acid in solution, lots of H2CO3. We increase the pH. Now there's going to be more HCO3 minus. We increase the pH even further. Now it's basically going to be all of the carbonate because it's a really basic environment. So now let's look at the question and see if we can interpret this diagram in relation to the question. So the first question is determine the Ka values for the species of H2CO3. So we want to find what the Ka values are for H2CO3 and HCO3 minus, so the two different dissociation steps. So let me erase my writing and let's sort of see if we can figure this out. So basically we have H2CO3, and we want to think about Henderson-Hasselbalch HH equation, right? If we remember, pH equals our pKa plus log of our base form over our acid form, right? Let's look at, and remember that we have pH equals pKa when our base form equals our acid form, right? Because then this log term basically disappears. So maybe we can find a pH that satisfies this base form equaling the acid form, right? If we can find where the base form equals the acid form, we can take that pH, and we know that that pH is equal to the pKa. So let's use this sort of reasoning to look at this diagram and figure it out. If we have the fraction of species being half, so say we have H2CO3, and we're looking at the fraction of the species of H2CO3 being half. That means the other half is basically only HCO3 minus. Why is that? Because it's in an acidic solution, which means that carbonate is going to be basically non-present because our pH is not in the range where carbonate is prevalent in the aqueous solution. So if we look at this and we take a fraction of species being 0.5, that means, so if there's 0.5 H2CO3, that implies that the other 0.5 is HCO3 minus. This is because the amount of carbonate CO3 2 minus is basically 0 because the pH is acidic, and compared to H2CO3 and HCO3 minus, it's going to be not present at all, right? So it's going to be such a minuscule amount that we don't even have to worry about it. So this, where the fraction of species is 0.5 for H2CO3, that means the base form and the acid form are equal, which means that our pH is going to equal pKa1. So if we we look at the vertical and we see our pH, we can sort of approximate. It's a little bit difficult to approximate, but I approximated this as 6.5, which means that our pKa1 is approximately 6.5. So that's the pKa for the first dissociation step. Now we want to look at the second dissociation step. We do the exact same thing. Let's look at where it's 0.5, but this time we're looking at 0.5 of HCO3 minus. If we look here, we can see this is 0.5 HCO3 minus. And we can see, if we drop a line down, we can see what this pH, this pH is pretty high, right? It's between 10 and 12. That means it's quite a basic environment. We're going to have virtually no H2CO3 because H2CO3 is only present in an acid environment. So, because this is in a basic environment, the only two species that are worth considering, this is sort of where your assumptions have to come in. The only two species worth considering are the HCO3 minus and your CO3 2 minus. So the other 0.5 is going to be your CO3 2 minus. So again, at the spot, we know that the pH is going to equal the pKa. You have to try and approximate this pH. It's quite a hard diagram to sort of exactly approximate, but this is about 10.3. So that's how you would use this diagram to sort of figure out the Ka values. Basically, you want to look at your Henderson-Hasselbalch equation, figure out when pH is going to equal your pKa, and that's how you can find your pKa's pretty easily. Next question, what carbon-containing species is dominant based on the 4 equilibrium constants? So, to actually finish out 3.1, technically it asks for the Ka values, so let's go and write in the Ka values up here. So we have Ka1 being, the pKa being 6.5. That means that for the Ka, it's going to be 10 to the negative 6.5, which is approximately 3.16 times 10 to the negative 7. And for Ka2, we have this as 10 to the negative 10.3, which is approximately 5.01 times 10 to the negative 11. Hi guys, sorry for the weird cut, but I just realized there was a typo in this question. So if we look at the equilibrium constants that were given, we can see that this first one, the units of the equilibrium constant are atmospheres over molars. And when we look at our expression, we have molars over atmospheres. So our KH1 is actually equal to, our 29.76 is actually equal to the PCO2 divided by the concentration of CO2. So we just need to keep this in mind for a future question. That was just a little mistake they had in the question. But let's continue to 3.2. What carbon-containing species is dominant based on the 4 equilibrium constants? So we can see that the first equilibrium constant just tells us gas to CO2 in solution. So we're basically looking at the dominant thing in solution, right? We don't really care about, obviously there's going to be more CO2 in the atmosphere than there is in solution, just because there's so much, like that's the entire sort of bank of carbon dioxide is in your atmosphere, right? So basically CO2 is starting off as the winner, right? We're gonna the concentration of CO2 we're gonna assume is the highest, and we're gonna see if something else beats it, right? So let's look at the next equilibrium where we have this CO2 aqueous forming carbonic acid by reacting with water. If we see that we can see that this KH2 is 1.7 times 10 to the negative 3, which is much less than 1, which means that the concentration of carbonic acid over CO2 is much less than 1, which means that CO2 concentration is much greater than the carbonic acid concentration. So we've now said that with this equilibrium constant, CO2 is still the winner. So we're going to keep that as our winner. Now, if we look at the next sort of 2 equilibriums, these equilibriums have to do with the dissociation of carbonic acid. Remember, H2CO3 is a weak acid, right? And because it's a weak acid, that means it's barely going to dissociate, right? It's only going to partially dissociate, and you see that with these really small Ka values. Because the Ka values are really small, it tells us that H2CO3 is only partially dissociating. Because there's already so little H2CO3 compared to CO2, there's going to be even less HCO3 minus and CO3 2 minus in solution than the H2CO3, because H2CO3 is a weak acid, right? There's not going to be much of the base form when you put carbonic acid in, because it doesn't dissociate much. So because of that, we know that CO2 is still the winner, and our final answer for 3.2 is that CO2, our aqueous CO2, is dominant. So now let's look at our next question. In 2011, a number of measurements were made of the water CO2 concentration, and it's telling us that the average atmospheric P of CO2 level was 450 parts per million. Now, in the atmosphere, right, we have 1 atmosphere of pressure, which is sort of self-explanatory. The atmosphere is the amount of pressure in the atmosphere. So we have 1 atmosphere of pressure. Now we got to think about what does parts per million mean, right? Say I wanted 1 part per million. That basically means that I'm treating this 1 atmosphere as 1,000,000 parts, and I'm figuring out what 1 in 1,000,000 of that is, right? So if I treat 1 atmosphere as 1,000,000 parts, 1 part is 10 to the negative 6 atmospheres. That's 1 part per million, right? Because 10 to the 6th is 1,000,000. If I want 450 parts per million, I just multiply this by 450. So 450 times 10 to the negative 6 is the pressure of CO2 in atmospheres. So now we can use this sort of value and plug that into our equilibrium expressions. If we look above, this was where the typo really was noticed, right? Because you have to use this KH1. So we have that KH1 is equal to PCO2 divided by a concentration of CO2. We know what the pressure of CO2 in the atmosphere is, so we can solve for the concentration of CO2. And how do we do that? Concentration of CO2, if I move this around, right, switch these two, concentration of CO2 is equal to the P of CO2 divided by KH1. So let's write that here. We have concentration of CO2 is equal to the pressure of CO2 divided by KH1. which is equal to 450 times 10 to the negative 6 atmospheres, divided by KH1, which is given as 29.76. And if you do all this math, you'll get that this ends up being 1.51 about times 10 to the negative 5. So this is what you'll get for your concentration of CO2, 1 molar, obviously. So here we go. That's our answer for 3.3. And it also asks us to state the assumptions used. So what assumptions did we use? The key assumption that we used is parts per million actually depends on mass. It's like a mass percentage rather than a mole percentage. So if we look at what we did, we took this 1 atmosphere, and remember, pressure is proportional to the number of moles, right? If we look at the ideal gas law, PV equals nRT, we have pressure being proportional to the number of moles. So when I did parts per million with pressure, when I said, okay, let me just divide this pressure into 10 to the 6th, I'm looking basically at, let me divide the moles by 10 to the 6th. But parts per million has to do with mass. And we don't know that everything in the atmosphere technically has different molar masses, right? Nitrogen has a different molar mass than oxygen, has a different molar mass than CO2, and etc. So we kind of assumed that we can everything in the atmosphere has a really similar molar mass, so that we can just assume that 450 parts per million is the same thing as 450 parts per million of the moles, which is the same thing as 450 parts per million of the pressure. So that's one thing that we assumed. We assumed that the molar masses are similar enough for us to just look at sort of the mole fractions rather than the mass. So that's basically the assumption that we used. Now let's go on to 3.4. Theoretically, adding H2CO3 to water will create an equilibrium between carbonic acid, carbon dioxide, and water, right? This system can be relatively complex and can be simplified by assuming that the carbonate ion concentration is approximately 0. So this is where I said in the beginning, they sort of give you the assumptions that you need. If this was an actual if this maybe was a SChO problem or something like that, they would expect you to be able to figure out these assumptions by yourself. That's why I think this is a really, really good beginner mass charge balance problem that sort of gets you going on how to solve MCB problems without trying to force you to do too much, right? So let's do this question, 3.4. Show that the composition of the solution is fully determined by the pressure of CO2 by finding an expression for H plus that has pressure of CO2 as the only variable. Okay, so what we always want to do is write mass balance and charge balance, right? So let's write charge balance. That's easy. Charge balance is basically saying that everything in solution in total must have a net neutral charge, because you didn't add charged things to begin with. You started with something that was neutral, and so you need to end with something that's neutral. So charge balance is just saying all the positive ions in solution must be equal to all the negative ions in solution. The net charge of both must be equal. So we look at our positive stuff and we look at our negative stuff. Our only positive thing in solution is hydrogen ion. So our H plus concentration, that's our positive side, so I'm going to call this the positive side, is equal to, now we got to look at our negative side. Our negative side has the HCO3 minus plus carbonate plus our hydroxide. Okay, but carbonate is 2 minus charge, right? So we need to put a 2 in front of here. And basically that's just because we have this, right? We need double the amount of hydrogen ions to account for a 2 minus charge. We need double of a positive 1 plus charge to account for 1 of the 2 minus charge. It's a little bit confusing, but it makes sense when you sort of try and reason it out that way. So we have this 2 in front, but what did the problem say? The problem said we can assume that this is approximately 0. And note that this entire side is the negative side. So we can assume that this carbonate concentration is approximately 0. Because, why can we assume that? Because we're in sort of like an acid solution. We added only carbonic acid to begin with. That means our solution is acidic, which means that the amount of carbonate is going to be very, very, very small. So that's why we can assume it's basically 0. If we write this out, we get H plus equals HCO3 minus plus OH minus. I'm going to put an approximate sign here. And we know that OH minus, if we know our KW expression, we know KW equals H plus times OH minus. So basically, because I'm trying to find a formula for H plus, right? What is the question asking? The question is asking, we want to find an expression for H plus that has PCO2 as the only variable. So we want to only have H plus and pressure of CO2. And we have this relationship between H plus and OH minus. So I can rewrite OH minus as KW over H plus. And so I can write this as HCO3 minus plus KW over H plus. Okay, so now we need to rewrite HCO3 minus in terms of something else that we can use. Like maybe we can look at our equilibrium constants and see if there's something we can rewrite HCO3 minus as. So let's look up at our equilibrium constants. We can see here, right? We can see Ka1. If I rearrange Ka1 to solve for HCO3 minus, remember we want to replace HCO3 minus with something that comes closer to pressure of CO2. So how I would think about this is, if we rewrite HCO3 minus with Ka1, we get some function of H2CO3, carbonic acid, right? When we move stuff around, we get some function of carbonic acid and our hydrogen ion. We want our hydrogen ion. Now we just need to get rid of our carbonic acid and make it pressure of CO2. With KH2, this equilibrium, we have a relation between carbonic acid and aqueous CO2. And with KH1, we have a relationship between CO2 and pressure of CO2. So basically, if I use this Ka1, I can eventually get to something with pressure of CO2 and H+. So let's try it, right? We can write HCO3 minus here. I'll use the Ka1 expression. So you get Ka1 times H2CO3 divided by H+. Now, say we want to rewrite H2CO3. We can rewrite H2CO3 looking at our KH2. If I move this CO2 there, we can rewrite this as KH2 times the CO2 concentration. So Ka1 KH2 times CO2 concentration divided by H+. And finally, if we look at our last equilibrium, right, KH1, remember that we want to look at this guy here, right? We have that CO2, concentration CO2, is equal to the pressure of CO2 divided by KH1. So let's replace that again. Ka1, KH2, pressure of CO2, and then we have this divided by KH1, and we also have our H+ term. So now we've gotten our HCO3 in terms of pressure of CO2 and H+, which is exactly what we wanted. So let's sort of copy this down below, right? Let's copy this down below. So I'm just going to copy this, or let me just move it actually. I'll move it. But yeah, so basically you see what we did. We just solved for HCO3 minus in terms of things we actually wanted to solve for. So if I rewrite this here, we'll get that HCO3 minus, we get Ka1 KH2 over KH1 times pressure of CO2 divided by H+ plus our Kw divided by H+ equals our H+. So what can we do now if we want to solve for H+? I can multiply both, this is just algebra, I can multiply both sides by H+. We get H+ squared is approximately equal to Ka1 KH2 over KH1 PCO2 plus our Kw term. And then I take the square root of both sides. You'll get H plus is approximately equal to the square root of Ka1 KH2 divided by KH1, pressure of CO2 plus my Kw. So basically, this is how we solved for our H plus concentration. You can see that all we did, right, we first set up our charge balance. We then made an assumption that was sort of given to us. We made the assumption that carbonate is 0. Then we tried to rewrite the stuff we didn't want, right? We don't want HCO3 minus. We don't want OH minus. Use your equilibrium constants to rewrite those in terms of terms that you do want, right? We rewrote this guy using 3 different equilibrium constants in terms of our pressure of CO2 and our H plus. We rewrote this guy in terms of H plus through our Kw, right, our water dissociation equilibrium constant. So basically the main takeaway is look at the terms you have, try to eliminate the terms like carbonate that you don't need because they're very close to 0 or they're very minuscule, then rewrite stuff using your equilibrium constants. And then only do you actually solve, right? So hopefully that made sense. Let's look at the next question now. So that's our expression for H plus. It's right here. I'll just box it. Okay. Determine the pH of the simple system mentioned above. If you had not yet solved x.3 or use the expression H plus. Okay, so I think that's referring to if you had not solved this guy as of yet. If you didn't get an answer for this, then you can use that equation. So let's determine the pH. How do we do this? So basically it's saying in order to be able to model an ocean, the starting point is a simple system. A glass of pure water is placed in open air, then you have an equilibrium. If you place the water in open air, you're basically exposing the water to what is the pressure of CO2? 450 times 10 to the negative 6 atmospheres. So basically, we know that this is the pressure of CO2 when we expose water to the open air. The open air has this pressure of CO2. And we have a whole formula that, that gives us H plus concentration in terms of pressure of CO2. All you have to do is go through this, look at the formula you have, and plug in pressure of CO2 is 450 times 10 to the negative 6. And then you'll get a concentration for H plus, and you want to take the negative log of that. So you basically want to take, if I write it out, pH is going to be equal to negative log of square root Ka1 KH2 over KH1 times the pressure of CO2, which we're given as 450 times 10 to the negative 6, plus our Kw term. And if you plug this all into your calculator, you should get a value. I got 6.87 as my pH. So that shouldn't be too difficult. That's just a plug and chug question, given that we got this answer correctly previously, right? I think this was the main difficult part of the question. And then the next part was just this part where you just found the pH was just a little bit of plug and chug. Now let's look at 3.5. Or not 3.5, 3.6. So let's read this. Normally the pH of is around 8.1. In connection with an increased emission of carbon dioxide, right? So basically we have more carbon dioxide emissions in the atmosphere. That's going to increase the pressure of CO2. This increase in the partial pressure affects the equilibria system. And if you remember here, our H plus concentration is sort of proportional in some way, right? As my pressure of CO2 goes up, you can see mathematically that my H plus concentration is also going to go up, right? And that sort of was also there intuitively because the more CO2, the more carbonic acid. So our H plus concentration is going to go up when our pressure of CO2 goes up, which means that the pH is going to decrease when the pressure of CO2 goes up. So we can see that the increase in the partial pressure affects the equilibria system and the pH value decreases. Figures 3.3 and 3.4 show correlations between the average values of the partial pressures of CO2 and the pH. So this is just showing the CO2 pressure over time, and you can see how it's increasing pretty rapidly in the 2000 to 2010 range. And the next thing we see is the pH over time, and again you can see just like how because of the CO2 increase, we can see that pH is decreasing at pretty rapidly as well. Next, in 3.6, it's saying that explain which of the following types of functions the solubility of carbon dioxide and pH follows. This is a very, very easy question. I kind of overthought it when I was initially doing it, but we can see that in these diagrams we're given that y, or our pressure of CO2, is equal to some sort of quadratic, right? We have x squared, x, and a constant, right? X squared, x term, and a constant, right? And so we have a quadratic. So the solubility of carbon dioxide is going to have a quadratic or polynomial function, right? And pH we see is the exact same thing. We have x squared, x, and constant. That also has a quadratic or a polynomial. So both of them are following a polynomial. So you kind of just can explain. You really don't need to explain much for this question, but basically just say that they both follow a polynomial, and we see this because because the function that's given is a quadratic, right? It has an x squared, x, and a constant term. Okay, if the development we see in figure 3.3 and 3.4 continues, so if our CO2 keeps going up, if our pH keeps going down, it'll have a catastrophic effect on our marine environment. Determine how many years from 2010 it would take for H2CO3 to make up 95% of the acid species in the water. Assume that temperature is constant, which means that nothing else is sort of variable, that we don't have to worry about any other factors, but just that this sort of curve is going to follow with time, right? This sort of quadratic modeling curve is going to keep happening with time. So let's think about this, right? H2CO3, if H2CO3 is 95%, that means this solution is really, really acidic. That means that the other 5% is going to be HCO3 minus. And again, this is because, remember that in an acidic environment, carbonate, or CO3 minus, cannot really, there's very, very, very little of carbonate, because that in a basic environment that would be prevalent. In an acidic environment, these two will be the prevalent ones, right? So the rest of it, the 5%, is not going to be carbonate, it's going to be our HCO3 minus. The next thing we can do is we can use Henderson-Hasselbalch. So we know that pH equals pKa plus log of our base over our acid. We're going to use HCO3 minus over H2CO3. And because we're looking at this base and this acid, we know that this is the first pKa, because the first pKa has to do with the dissociation of H2CO3. The second one has to do with the dissociation of our HCO3 minus. Then if we take this and this equals pKa1 plus our log of, because HCO3 minus is 5%, we can do 0.05. The other one is 95%, so 0.95. And now you would just plug this into your equation. So we know that pKa1, remember we found it way up here, is around 6.5. So we can plug this in, about 6.5. We plug this in and we get that the pH is approximately 5.22. So that's what our pH is when H2CO3 makes up 95% of the acid species. Next, we want to find how many years from 2010 it's going to take, right? So we know that this is the way that pH varies over time. And we know that what we're asked our pH should be, right? Our pH needs to be 5.22, and we know how pH is varying over time using this equation. So let's use this equation and set it equal to our 5.22. We can set our 5.22 equals this this entire quadratic, right? Our negative 0.0001 x squared plus 0.4372 x minus 423.46. And we can solve this quadratic using whatever methods you want. You subtract 5.22 on both sides, and then you have a quadratic that you can just find the roots of using the quadratic formula. But you'll get that x is about 2887.3. And this, we're asked for the amount of years after 2010, right? We're asked for amount of how many years after 2010. So this is the actual year. If we want the amount of years after 2010, we just subtract these. So minus 2010. And we should get approximately 877 years from 2010. So that's our final answer for our last question. So 877 years. Okay, so that's this entire question. That's question 3 from the SChO Silver. I hope this was useful to you. I think this was a really good intro mass charge balance question. It helped get introduced to the idea of setting up charge balance, setting up those types of equations without it being really difficult, and without there being a huge number of equilibria, and without it having so many unknowns that it's just sort of overwhelming at first. So yeah, I really think this is a good intro problem. Thank you guys so much for watching, and I'll see you in the next one.